Hey chemists, here we are with a little bit more London dispersion forces and also introducing dipole-dipole intermolecular forces. And so I believe that this table should be familiar to you from last lesson. Once again, when we compare a trend in boiling point or melting point, we are trying to compare molecules that that are similar. It would be impossible to compare, or atoms, it would be impossible to compare the boiling point of this molecule, this compound, propane, with a halogen such as iodine. They're completely different. So here we're comparing two organic molecules, propane and ethanol. And we notice that the molecular mass is similar. And we notice that propane has a boiling point of negative 42. Ethanol has a boiling point of 21. Let me bring down my Spumoni slide here. So here we go. In nonpolar molecules, propane's nonpolar. It's a hydrocarbon. Notice only carbon and hydrogen. Ethanol, again, topic 10, is a aldehyde, and the functionality of the aldehyde, as you will learn, is this carbon double bonded oxygen called a carbonyl with a hydrogen. We've already learned in nonpolar molecules we have only London dispersion forces, but we have discussed that in polar molecules the type of intermolecular bonding is dipole-dipole, and there is always underlying, no matter if you have a when you have a polar molecule, that London dispersion forces exist as well. They are the only intermolecular force that is present in nonpolar. But in polar, you have dipole-dipole interactions and your London dispersion forces. Sometimes this is called permanent dipole because they are permanent, they don't go away. Propane is a nonpolar molecule and ethanol is a polar molecule. Notice we have a very electronegative oxygen atom in this molecule, and this electronegative oxygen is going to pull the electrons in this double bond closer to it, therefore creating a permanent dipole within the molecule. And if we were to draw that permanent dipole, it would be, let's see, like that. Toward the carbonyl, toward the oxygen. I have no idea what that is. Okay, it just got erased. It's all right. Look at the boiling point. So we say, great! If I compare a nonpolar molecule and a polar molecule of equal or comparable molecular mass, I can predict that the polar molecule will have the greater boiling point, and that indeed is the case. So this is just reminding you of what I just said. Here are these two molecules being compared. Oxygen, again, electronegative, pulling the electrons closer to it. And the trend being, if two molecules of similar molecular mass are compared, the polar molecule in general, most of the time, but of course in chemistry there are always exceptions, is going to have the higher boiling point. The greater the intermolecular force, the greater the energy required for that change of state to occur. And dipole-dipole interactions are a stronger intermolecular bond than London dispersion forces, which are the weakest. Okay, let me get rid of that. Let's go to the next one. we're not comparing we're not comparing organic molecules anymore. Now we're comparing, okay, we have two compounds that consist of halogens only. We've got bromine, and then we have iodine chloride. Molecular masses similar, bromine nonpolar, iodine chloride polar. Great! The trend for boiling point holds. Fabulous. All right? So once again, I'm comparing a different types of molecules, but they're similar. They both have halogens. They both have similar molecular masses. We could absolutely not compare ethanol and bromine. Organic compound with a molecular mass of 44, bromine, an inorganic compound with a very high molecular mass. It's not possible. All things considered equal between the comparisons. Okay? We might assume that since bromine is nonpolar and ICl is polar, iodine chloride would have the higher boiling point, and we are indeed correct. And now, so we put that all together and we say, great, all right, we are going to, let me get rid of that. Now we've got, once again, a halogen comparison, bromine, chlorine monofluoride, bromine monofluoride, and chlorine monobromide. ClF, BrF, ClBr, and Br2. Now notice, very different molecular masses, okay. All halogens, okay. So you think, great, they're all halogens. I'm going to go with my molecular, so I have a couple of things to look at. Let me just step back. We have a couple of things going on. First of all, bromine is nonpolar. The others are polar. However, bromine's got a much larger molecular mass than any of the others. So we have a couple of things going on here. So we can't necessarily make a prediction. And in fact, our prediction, if we were to pick the polar molecule, because didn't I just say up above, in general, if it's polar, it's going to have a higher boiling point. Well, that theory just got shot down because this is the highest molecular, the compound with the highest molecular mass, and it is in no way the compound with the highest boiling point. We could look at which one is most polar. Okay, that might give us, bromine and chlorine, bromine and fluorine, and look at the electronegativity difference. But all of that aside, we see that bromine, nonpolar, okay, that really flies in the face of what we've just discussed up above, and it has the highest boiling point. So, what do? We have to be really careful about how we are comparing things. And we wouldn't necessarily be able to predict this without additional information. However, the fact that bromine is nonpolar does not give it a lower boiling point as opposed to any of the other polar molecules, and we see that it has the highest. And what really is at play here, although we might not know that if we weren't given any of this information, if we were just comparing that, we might not get the right answer. And it turns out that it is really the molecular mass that dictates the fact that bromine will have the highest boiling point. So when we can compare things that are similar without combining too many different things, in this bottom chart we are combining both polar versus nonpolar and a variety of different molecular masses, and it's really hard to determine. Whereas here, both molecular masses are similar, both are halogens here, both are organic compounds, and then we are able to effectively make a prediction about which of the compounds might have the higher boiling point. Okie dokie. That's all for now. Hope that was helpful.